So now that we've seen that we're pretty well convinced that dark matter exists, so what is dark matter? The ideas of what dark matter could be tend to fall into two categories. The first one we're going to talk about is that it is actually made of ordinary matter, meaning the stuff that we're familiar with, the stuff that makes up the Earth and the stars and the interstellar medium, all of that stuff. But it has been very, very compact into small objects that don't give off a lot of light. And these will need to be predominantly out in the halo of our galaxy to give us the correct rotation curve that we see. So these objects are called massive, compact halo objects, or machos. So one possibility for dark matter is that they're made up of machos. So some examples of what machos could be: there are brown dwarfs. So if you remember previously when talking about star formation, brown dwarfs are objects that form like stars that have enough mass that they're almost like a star in that they have fusion, but they didn't quite get enough mass to actually have fusion. So they still have a lot of mass, but they are cold and don't give off a lot of light. Another possibility would be a cold white dwarf. So a white dwarf is one of the stellar remnants, one of the things that stars turn into, particularly a low mass star will turn into a white dwarf. And if it's cool enough, these things are relatively small, about the size of the Earth. If it's cool, it's not going to give off a lot of light, but it still has a lot of mass. Similar with neutron stars and also black holes. So all of these things would be considered possibilities for machos. All right, here is another question to see if you've been paying attention. What is gravitational lensing? A, bending of light due to gravity. C, reddening due to gravity. C, the change of gravity due to the curve of space. Go ahead and think about it, and we'll discuss it in just a second. All right, so the correct answer is A, the bending of light caused by gravity. So we can actually use gravitational lensing to search for machos. Remember, the whole point is that we can't see the macho itself, but it will still have a lot of gravity, so we should be able to see it because of its gravitational influence. And so the idea is that we look out towards the halo, find a whole bunch of halo stars, and survey them, watch them over a long period of time. If a macho crosses between us and the halo star, then the macho's gravity will actually cause the starlight to focus onto the Earth. So from our view, the star will get brighter for a time until the macho has moved out. So we can actually do these surveys searching for these machos. Well, when we do, and we count up how many machos detections we have, and we can use some statistics. If we take the very most optimistic numbers, so skewing the statistics in the most favorable possible way, then machos make up about 10 to 20% of the missing mass. This is not nearly enough to account for the dark matter that we actually see. And again, this is the most optimistic view, taking the extreme error, saying that it's actually in our favor. So the other possibility for what dark matter is that it is made up of weakly interacting massive particles, or WIMPs. So we know it's not machos, so it has to be WIMPs. Now, the idea of a WIMP is that these are subatomic particles. So think things like electrons, protons, neutrons, neutrinos, but they're not of the normal variety that we're familiar with, the ones that make up atoms and so on. And in fact, if you take your favorite branch of theoretical particle physics, we actually have candidates for what some of these WIMPs could be. So there's a type of neutrino called a sterile neutrino. There are little particles called axions, all sorts of stuff that could possibly be. Now, so what we can do is we can then devise experiments to search for that type of WIMP, to see if it actually exists. Now, for every instance that we have done this, we have never found them. We have been doing this for over 40 years, and in every single case, we have turned up empty. Okay, so what this means is we know that dark matter is not machos, which means that it should be wimps, but we have yet to be able to find out what wimp it actually is. Although we don't know exactly what dark matter is, that doesn't mean we don't know about some of its properties. Okay, so we can actually look at astronomical things to figure out some of the properties for these small particles. Okay, so in this image, what we're looking at is the bullet cluster of galaxies. This is actually two galaxy clusters. We have this cluster on the left, and then another cluster over here on the right. Now, what's interesting about these clusters is they've actually passed through each other relatively recently. Remember, we're talking in astronomy, so we're talking within the last 500 million to billion years. Hey, so these two clusters have actually crashed through each other. Now, what's interesting is how it is that things have separated. So to help understand what we're looking at in this picture, the yellow, those are the galaxies. Okay, so this is the luminous matter. This is where all of the stars and interstellar medium is. The pink region are these regions of hot interstellar gas or intergalactic gas. Okay? Because of interactions between galaxies, they can actually have this intergalactic gas that's in between them within the cluster. That's what this pink stuff is. Okay, then the blue regions, this is where the dark matter has to be located based off of gravitational lensing. So we know where the galaxies are, we know where the intercluster gas is, and we know where the dark matter is. Okay, so what's interesting is when we compare the dark matter to the intercluster gas. Okay, so the dark matter stayed moving with the galaxies, but the intercluster gas has actually been slowed down and kind of separated from the rest of the cluster. The reason why this gas has been slowed down is actually because of pressure. Okay, so as the two clouds passed through each other, the gas pressure of these two gas clouds slowed each other down so that they didn't move as fast as the galaxies barreling through. Okay, well, what's interesting is that that same thing did not happen to the dark matter. The dark matter just kept going through. What this tells us is that the dark matter does not feel pressure like the intercluster gas feels pressure. So that the pressure that the intercluster gas feels actually comes from the electromagnetic interaction. So this tells us that dark matter does not interact electromagnetically. Okay, it is not charged. It does not feel charge. Now, if you remember way back, you hopefully learned that light is an electromagnetic wave. It propagates because of the properties of electricity and magnetism, and it interacts with matter because of the properties of electricity and magnetism. So if dark matter does not interact electromagnetically, it cannot interact with light. Okay, so it does not give off light, but it will also not absorb any light. Okay, so in my opinion, a better name for dark matter would actually be invisible matter. Okay, because it does not interact with light in any way.